Hello, students. Today we want to talk about absolute value of real expressions and how the absolute value impacts equations and inequalities. As you continue to study STEM mathematics in preparation for the calculus sequence, you're going to find that absolute value is very important. So we want to introduce some ideas that can help you as you continue your education towards the calculus sequence. Now, again, absolute value is something that you acquire really over time. Proficiency with it initially can be a little difficult because it requires you to rethink how you look at inequalities and equations because it does have a big deal to do with sign of an expression. Just like when we solve inequalities, we have to pay attention to sign, and paying attention to the sign allows us to solve inequalities correctly. So that's exactly what we're going to do with the absolute value. So let me share my screen. What I've done here is I have recorded some important ideas about the absolute value. And what I've done is I've started with the definition. Now, when it comes to absolute value, we have an interesting set of symbols. That is, what we do is we look at, let me adjust this just a little bit. There we go. This symbol here is the expression X with two vertical lines. Now, you notice here I've written U's and I've written A's and B's. Whatever expression we have can be denoted by any letter you like. So when we look at this absolute value, we're looking at real expressions. So I can say X is element of R. Now, of course, this also works with imaginary units and complex variable expressions, but we're going to just focus on real expressions here. So if you ever continue into other courses, the absolute value will follow you. Now, the best way to define it, at least initially, is by this function in two pieces. That is, the absolute value of X, as I've written here, is always non-negative. And so when X, the expression X, is greater than or equal to 0, then its absolute value is X. Now, when you think of X as just being a number like 5, we say the absolute value of 5 is 5. Now, if the expression is less than 0, then we take the additive inverse. That is, the absolute value of X is now the additive inverse of X. And of course, if you have an expression that's negative and you take its additive inverse, then you clearly make it positive. So don't think of the negative sign or the additive inverse sign here symbolizing that the expression is actually less than 0. It really depends on the context. So we take the absolute value of X to be the additive inverse of X when the X is less than 0. So that's something that will take a little bit of getting used to, but I think you can see if you compare this to a real number, like the absolute value of -3 would be the additive inverse of the additive inverse of 3. Or sometimes you say the negative of the negative of 3, which is 3. So that's why it's important to understand what this means in context to the fact that the expression X is less than 0. Now, another thing that's important or useful is to sometimes write the absolute value of X as I've written here, the principal square root of X squared. Usually when we think of taking the square root of X squared and using the laws of exponents, we look at the 2 and the 1/2 as absorbing. Now, of course, before, when we were getting rid of radicals and we were squaring, our algebra was exactly the way we needed it to be. But when you flip it around and you're actually taking the square root of X squared, then that defines the absolute value of X, because this is a non-negative quantity. So like before, when we would have the expression u squared, that would relieve us of the radical because the tacit assumption was that the square root of u was well defined. Now we're flipping that. And so we are forcing the non-negativity on this expression, and therefore we must replace the square root of x squared with the absolute value of x. And you'll find this to be useful, maybe not as often as you would like, but as you continue in your courses, there will be many opportunities to use this expression as an alternate to the absolute value of x. Now, what I've written here are some very useful theorems and also some properties of absolute value. Now, we're going to show why some of them are true, and then others we're just going to use. And I would encourage you to work with some of these to get a good feeling of confidence working with them. So now what we're going to do is start with a real expression, u, and we're going to fix a positive real number. What I'm saying here, when we fix a positive real number, it is a positive constant. So it's a number that's greater than 0. Now, what we want to see is how the absolute value reacts in equalities and inequalities. The first one that we do come in contact with is the absolute value of u equals the positive constant. Now, what that means is that we have an equation that we would normally think we would have if the absolute values did not exist. That is, if there was no absolute value, u equals c, and we would solve that. Now, due to the fact that we have the absolute value, we have to consider the case when u can possibly be less than 0. And then that would introduce a negative u, which can be transposed by multiplying by -1 to give us u equals -c. Now, let me just throw this out as just a word of caution. As I said before, when we take an absolute value of an expression, that expression can possibly change sign. And so when we take its absolute value, we have to consider this particular case. Now, if the expression is never negative, okay, then this case would not have a real solution. And so don't worry that if you make up a problem and you try it to solve it via this theorem, that you don't always get a solution for every case. So that's just the nature of what we're working with. So for instance, here's an example. I'll put a little example here. Say you had the absolute value of x squared plus 1 equals 2. Okay? Well, x squared plus 1 is non-negative. That is, notice, it's actually always positive. So x squared plus 1 is always positive. So when we think about this, we look at this and then consider this particular side. We would know that this would never have a solution. So if we took this theorem and said, okay, well, we'll look at x squared plus 1 equals 2, which we could solve by factoring or the square root property, or x squared plus 1 equals the additive inverse of c, which in this case is -2. So now, of course, we have x squared equals -3. Now, of course, we know that this has imaginary zeros, but it has no real zeros. So for instance, here, we would say no real zeros. So what I'm emphasizing here is that when we consider absolute value, we are basically considering ordered properties that we have with real numbers. Now, if the problem specifies that find any solution, solve in the complex numbers, that's fine. But the whole idea of the absolute value, at least in this case, is to consider the fact that the expression can change sign. Now again, when we think about absolute value with complex numbers, we're thinking of calling it the modulus. And when we look at an expression, we have the square root of the real part squared plus the imaginary part squared. So there are all other kinds of things that we can consider, and we can also think about different contexts. So when you solve problems like this, for now, we will be looking for real solutions. Now, don't worry that later on you may change the actual hypotheses of the problem and then be able to say other things. I just want you to be aware that in this case, if we wrote the theorem down here, there would be no real zeros. So that wouldn't give us anything new if we were restricted to real solutions. Now, another one that's very popular in the calculus, as all of these are, is this particular expression. That is, the absolute value of u is less than a positive constant c. Well, when we have that case, this gives us a symmetric interval about 0. That is, u will now live between the additive inverse of c and c. So you've got a positive number and its additive inverse and 0 right in the middle. And then u lives in that symmetric interval about 0. This is what we call the conjunction. The conjunction. Very useful in writing symmetric intervals in the calculus. Now, if we flip the inequality and have the absolute value of u greater than c, then we do, instead of having the intersection, so to speak, or a compound inequality, we get two separate inequalities. And again, we're back to number one, where, you know, it might be the case that the expression u never takes on any negative values. And if it doesn't, then we would not get any solution here. We wouldn't get a real solution. So the idea, and then we think about the fact that complex numbers are not ordered like the real numbers. So we always have to consider the context of problems and the actual number system where we're asked to solve them. So when you write this, as we've written this for number one, you just look at it and say, okay, well, this would not give me any real solution. So I'm done with that part, but maybe this one will. So just remember, the theorem gives you these equivalencies. That is, if you have the absolute value in this equality and these two inequalities, you can solve the equalities and inequalities that are listed here to the right as an interpretation of the absolute value. But that does not guarantee that each piece or any of the pieces will have a solution. Okay, so this is a way to interpret the absolute value, but it doesn't guarantee anything. It just says the interpretation would have to be this. And then you have to look at each case to see if you get a solution. Now, what I wanted to list here, and I just said useful fact, which I've already talked about, the absolute value is always non-negative. So I wrote a couple of cases over here that again, provide you with the empty set. For instance, as you've noticed up here, the C is a positive constant. So that's really what makes these have any kind of relevance at all to us. So we wouldn't think that any of these would make any sense if the C were less than 0, because by definition, the absolute value is non-negative. So if we had the absolute value of x minus 7 less than or equal to -3, there would clearly be no solution. There would be no solution even with the complex numbers, because the modulus is non-negative. So in cases where there's no solution, we just say no solution. And of course, the same thing here. If we had the absolute value of 3x plus 2 equals -4, well, again, the absolute value is non-negative. So there would be no solution here. So be sure that when you apply these results, that you are using the hypotheses here. Otherwise, these are not applicable. We have to make sure the hypotheses are satisfied. And another thing that's important here is that we see we have the absolute value of the expression isolated. So in order to actually solve these by this theorem, we have to isolate the absolute value. Now you can manipulate the U and then use properties of absolute value to rewrite things and then apply the theorem. That's fine, and I'll show you how to do that. But in order to do that, we need to know a little bit about absolute value. That is, if we've got two real expressions here, we'll just go ahead and keep that as our context. We will use the fact that the absolute value of a product is the product of absolute values. You can break up the product that's inside the absolute values and then apply the absolute value to each of the factors. So we say the product of, the absolute value of the product is the product of absolute values. So very useful. Likewise, if we're thinking about using this particular rule here, we can always flip around differences in the absolute value. For instance, you can always factor a -1, and of course, if we use this result, the absolute value of -1 is 1, and so it wouldn't matter which order we wrote here. It's kind of like a square. If you square the quantity x minus 2, that equals the square of the quantity 2 minus x, because it doesn't matter that if you flip the numbers around, you impose a negative, but squaring the negative is positive. Well, likewise here, if you take the absolute value of the negative, it goes away to 1, or it reduces to 1. And so the idea here is that this can be of use to us when it's more convenient to have the order written in a particular way. And the last one, I've drawn the triangle here. This is called the triangle inequality. If you think of sides of a triangle as being denoted, or their lengths as being denoted by absolute value, then you can see that any length of the third side, if we call it the third side or a side of a triangle, would never be greater than the sum of the other two. So for instance, we would always have that the third side, and I'll just call this the third side, has length less than or equal to the sum of the other two sides. So again, the triangle inequality is termed this way because you can think about this in a vector sense, where you add two vectors and then you have the resultant vector, which is the third side of the triangle. And then we have this nice inequality. Of course, you can prove this by means of arithmetic using the definition of the absolute value. But it is really convenient to think of this expression as to why this is true, at least in a geometric sense. So before we do some examples, I want to look at why, for instance, one direction of number 2 is true. Now, when it comes to working with absolute value, you use all of the tricks and all of the routines that you are aware of with the inequalities and the equalities. That doesn't change. We just see with the theorem that we have a way to interpret the absolute value. What I wanted to do is just look at one direction so you would have some understanding of why these theorems exist. And intuitively, they do make sense. So if we had the U, an absolute value is less than C, and C, again, is greater than 0, and it's fixed. It's a positive constant. And U is a real expression. So remember, context is everything. So what was the result? This means that U will exist between the additive inverse of C and C. So thinking about that and thinking about the fact that U could actually be positive and negative. So if we wanted to just prove one direction, let me show you how you would do that just using the definition of absolute value. So if we assume this and wanted to show that U was actually between the additive inverse of C and C, we could do it by cases. So this will be very helpful. And if you're interested in going in the other direction, you should try that, or you can come to Zoom or ask me about it to get some hints. It won't be very difficult once you see this direction. So first, we're going to think of U as being non-negative. Again, these are the cases we have to assume, even though in practice you may not have negative values. Okay, it may be such that it doesn't have positive values. It just really depends on the style of the function, so to speak. And what's interesting is that you're thinking with this absolute value in the properties, you could always absorb, you know, some negative factor or whatever, but we always just have to look at the context. So in this case, we can look at this and suppose this. So now we have the absolute value of U, which equals now U, because U is non-negative, its absolute value is just U, and these are equal, and of course the absolute value is less than C. So that means U is less than C. But then, of course, U is greater than any negative number because it's non-negative. So we would have that U is between the additive inverse of C and C. Kind of the last part's a freebie, because again, if U is non-negative, it certainly would be greater than any negative number, and the additive inverse of C is less than 0 by the hypothesis here. So we got that one. Now let's look at the part where U could possibly be less than 0. So what we want to show is that the absolute value of U less than C means that U is between the additive inverse of C and C. So now if we assume that U is less than 0, then we know that the absolute value of U is equal to its what? Additive inverse. But now, of course, the absolute value of U is what? Is less than C. So this is less than C. But now we need an expression for U, so we get to use our result that we learned for the inequalities. That is, now we want to basically isolate the U, so we're going to have to multiply both sides of the inequality by -1. So in doing that, we'll have, I'll just go ahead and write it out. We have -1 times -U will now be greater than -1 times C. Now I'm writing a lot of extra stuff here, but it's fine just to review it. And so that means we have U is greater than -C, or the additive inverse of C. But of course, U is less than 0, so it would have to be what? Less than any positive number. So now, not only is U greater than the additive inverse of C, it would certainly have to be less than C, which is positive, since it is negative. So what you're seeing here is that by assuming that the absolute value of U is less than C, we get U between the additive inverse of C and C in both cases. So that's how you would show that the direction that we've noted here is valid, just by using definition of absolute value. So again, just remember, we think of the absolute value as being a non-negative extension. And so it turns out to be extremely useful. Right now, it's just a little bit different maybe, but it has so many good uses for us. And if you're interested in looking at other parts of the theorem and the other properties, you can apply the same technique here and find that you'll get plenty of success in your calculations. Now, there will be some times when we want to apply the alternative form, and I'll show you that. So let's look at a first example. I want to just look at one where we have the absolute value inequality. So we have the absolute value of 2/3 x plus 6 equals 12. Now, one thing you notice here is that the absolute value is isolated and the 12 is a positive number. But I want to show you how you can factor inside the absolute value and then use the properties, because you don't have to suffer through this, but you can also look at this as saying, okay, well, I can treat this and factor this just like I'm solving any kind of equation or inequality and do that algebra. So let's, before we use the theorem, let's just operate on this because we can. So notice we'll factor the 2/3. And we'll have x, and then of course we'll have to multiply 6 by 3/2 because it doesn't have, it has the 2/3, but I'm just going to cheat and multiply it by 3/2. If I extract the 2/3, I want to be able to absorb that when I multiply, so I still have a 6. And now notice we've got the absolute value of a product, so we have the absolute value of 2/3 times the absolute value of this expression. So I'll go ahead and use that. And of course, you could just drop this out, but we want to go ahead and write that down. And then, of course, we have x. And of course, the 2 will absorb into the 6 to give us a 3, and 3 times 3 is 9. And this is equal to 12. Now, of course, the absolute value of 2/3 is just 2/3. So this gives us 2/3 times the absolute value of x plus 9 equals 12. Now, of course, when we solve an inequality, we can just multiply both sides by 3/2. X plus 9 in absolute value equals 12 times 3/2. And of course, the 2 absorbs into the 12 to give us a 6, and 6 times 3 is 18. So now we have the, and it's much simpler now. And this is kind of a good exercise to show that you understand, again, the absolute value of the product is the product of absolute values. That's a very useful tool in mathematics, and you'll find many uses for it when you work in more STEM math, and especially in the calculus sequence. So now we can apply the first part of the theorem. That is, we have the absolute value of u equals c, so we'll write both of these down. So now, equivalently, using the theorem, we'll have x plus 9 equals 18, or x plus 9 equals the additive inverse of 18. So now when we look at this, these are just simple equations. I mean, we don't even have to use zero product. We just do them because they're easy. So subtract 9 for both sides. I mean, you can do zero product, but these are so straightforward. We just go ahead and look at it this way, but your choice. And then, of course, if we subtract 9, x is negative 27. So we get two solutions, 9, negative 27. Now, here's the thing. When we apply these theorems, we don't really have to go back and check, because this is a direct use of a theorem. Each of these equations that we have here, we can either solve them or we can't. If you don't get a solution, then okay, there's nothing to add for one case. We get one here, then we're done. So what we found is in both cases, we have a legitimate solution. And so our solution set would include 9 and negative 27. Now let's look at an example where we have an inequality, but we have a more complicated argument of the absolute value. So x squared minus 3 in absolute value is less than 2. Now, of course, we know that the x squared minus 3 is quadratic. And when we look at this, we're thinking, well, this is set up for the conjunction. So the conjunction, the absolute value of u less than c, gives us u between the additive inverse of c and c, just like we proved up here, one direction. Now, what's interesting about this, if we write this as a compound inequality, we don't have the luxury of being able to solve this in a way without breaking down compound inequality into two pieces, because the nature of the square here is a little bit more difficult to predict. So of course now, if and only if, we'll have -2 less than x squared minus 3, but also greater than 2. Now, when you look at this and you think about how we're going to solve this, because of the square, we really do have to break it up, because you're thinking, well, you know, you could add 3 and then you've got x squared between 1 and a 5. And you look at that and say, well, is that gonna cover everything? Well, it actually does give us a way to look at this, at least in terms of part of the solution. But because we have the square, we have to think of doing a square root. And you might be thinking, well, okay, if we're squaring things, would our solution set also have some negative numbers in it? And the answer is yes. And so let me just write a few things here. Say, for instance, you just said, okay, well, if this is the conjunction, then we add 3 to all sides. So 3 minus 2 is less than x squared, which is also less than what? 2 plus 3. Okay, so now we have 1 is less than x squared, which is less than 5. Okay, so we at least have simplified it to this point. Now, again, when you look at this and you think, well, you know, we could try to work this with applying the square root, because that's an increasing function, and we would be good with that. But the issue now is that when we look at this, what's going to end up in between is an absolute value, because if we apply the square root, we'll have the square root of x squared, which is the absolute value of x. So that's where we're having to do some interpretation to make this work. And so if you have the absolute value of x between the square roots, you basically have to look at the two cases. So when you decide to break this up into two cases is really up to you. So again, let me just do this. Apply square root. So you could have started by looking at two cases from the very beginning. So the square root function is again an increasing function. So we have the square root of 1 less than the square root of x squared less than the square root of 5. So equivalently, we have 1 is less than the absolute value of x is less than the square root of 5. Now you can see why we're at this point forced to look at this one, this inequality, and this one, because we have the absolute value, because it necessarily takes into account the sign of x. Okay, so the main thing here is that I want you to see that we did a direct application of the theorem. Remind you of it right here. And then we said, okay, well, we can isolate the x squared, and then we can apply the square root, which we've done before. It's an increasing function, so it preserves the inequality. But the square root of x squared is the absolute value of x. So now what we have to do is look at this inequality and look at this and join them with the and we'll be done. So this particular theorem is very useful to us, but then of course it requires us to make some adjustments when we get to something that introduces another absolute value. So again, if you decided to break this up at the very beginning, you get the same answer. It just depends when are we going to look at the separate cases. So the first one here, we've got the absolute value of x is greater than 1. Okay, that's the disjunction. So we know how to solve that. We're ready to go. That is, now we have x greater than 1 or x less than -1. Let me show you. That's this one. That's the disjunction that we have here. the disjunction. And so now, of course, this would be negative infinity to negative 1 union 1 to infinity. Now, the next one here is the absolute value of x is less than the square root of 5. That is the conjunction. So let me just write this here. Disjunction. These are old terms, but they are very useful. Disjunction and the conjunction. We can think of conjunction as intersection together. We can think of disjunction as disjoint. So now, of course, equivalently using the conjunction theorem, x is between the negative square root of 5 and the square root of 5. So now we get negative root 5 to root 5. So this is an and. So we look for the intersection, but of course now when we do the intersection, we just run from negative root 5 to negative 1, union 1 to root 5. Root 5 being bigger than 1, negative root 5 being less than negative 1. So the intersection gives us the negative root 5 to negative 1, union 1 to root 5. So when you look at this, you see if we didn't have the absolute value, boom, right there. But because of the absolute value, we need this additional piece here. Now, of course, if you look at this and you think about how we have a pattern going on here, you could probably say, oh, well, that's going to be the answer when you see that if you have lots of practice working with these. But it's better to actually look at the cases just to make sure that your interpretation is right. So remember, even if we have a direct application of the conjunction theorem, then we still need to make sure that our application provides us with a correct solution. We certainly, this is part of the solution, but it's not all of it. So now we can break this up into two separate inequalities. And the and means, in this case, that is the absolute value of x is greater than 1 and less than root 5, gives us these two solutions that we must intersect to find the solution. Now, of course, if there's no intersection here, then there would be no solution. So just remember, the absolute value is very robust, but we have to respect that it is always a non-negative quantity. And because of that, as we apply our results, we keep that in mind. And this, like I said before, this sheet gives us many of the ideas that work very well with the absolute value when we have equalities and, of course, the inequalities, which we use both of these here. And then, of course, these rules are very useful, especially this one, as we factor things and then take the absolute value, the product, giving us the product of absolute values, so we can actually simplify the u and make the equation easier, like we saw in this problem. So you have plenty of flexibility when it comes to working with equations and inequalities, even if they have absolute value. So let's look at some more examples. Now, the next one that we want to do, let's just look at some more inequalities that have to do with the theorem. So in this case, we have the additive inverse of the absolute value of 3x minus 3 is greater than or equal to negative 8. Now, when you look at this, this doesn't really fit the theorem. The absolute value is not isolated, so we don't have a problem with that. But of course, to apply the theorem, we would need that. And so the first thing we can do, if you will, is just go ahead and remove the negatives. We can't just absorb them because this is an inequality. So to kind of give us an idea of what we need to do, we're thinking, well, to remove the negatives, we must multiply the inequality by a number less than 0, namely -1, which will reverse the inequality. So let's write that out just for practice. So we have -1 times the negative, absolute value 3x minus 3. Now reverse -1 times -8. You can always just say negative for additive inverse, since that gets a little bit long, but whatever you like to say is fine. So now, of course, the negative, of course, you can think of the negative as just -1. That gives us the positive. So 3, go ahead and factor the 3 from the two terms there. And we have less than or equal to 8. So now what you're saying is that we flipped the inequality. So this changes the notion of this description, right? For instance, if we have the absolute value is greater than some positive number, we call that the disjunction. But we couldn't really call this the disjunction because it wasn't in the right form. But now, of course, once we get rid of the negatives, this has the form of the conjunction. But now let's go ahead and use the product deal here. We've got the absolute value of the product. So just for practice, this will be the absolute value of 3 times the absolute value of x minus 1 is less than or equal to 8. And now, of course, the absolute value of 3 is just 3, so we can divide both sides by 3. So just remember, the absolute value of 3 just equals 3. So this will give us the absolute value of x minus 1 is less than or equal to 8/3. So now we're good to go. That is, one thing about manipulating the argument, we call that the expression of the absolute value, using the absolute value of the product is the product of absolute values. It does simplify things. So now we can just go ahead and apply the conjunction. Could have applied it here, but we wanted to practice with that result. I want you to learn how to do this because this is very useful. And so now we have the negative of 8/3 less than x minus 1 less than, well, we've got equal to, let me not forget that, less than or equal to 8/3. So now we can simply add 1 to all three sides. And if you will, just write the 1 as 3/3, since we have need a common denominator of 3. So we have -8/3 plus 3/3 less than or equal to x less than or equal to 8/3 plus 3/3. Okay, and so a -8 plus a 3 is a -5, so we get -5/3 less than or equal to x, and of course 3 plus 8 is 11, less than or equal to 11/3. So now we can just write that as a closed interval, -5/3 to 11/3 closed. So what you see here is, with this computation, even though it's very simple compared to the last one, we get to use the properties of the absolute value. And then we get to use the conjunction theorem, okay? So just remember that the absolute value is useful, and it will be your friend if you know how to manipulate it correctly. And what's interesting about the absolute value is that as you take the calculus, you'll find some reasons why you should continue to pursue it, because when you get the definition of limit in calculus, it will involve the use of conjunctions. And I will give you an example where you can practice with some symmetric intervals and see what I'm talking about. Now let's look at another one. So say we have the absolute value of 4x minus 3 is greater than or equal to 9. Now, of course, when you look at this, this is like ready to go. This is a disjunction, but let's do the same thing. What I've noted here is, let's go ahead and apply the same technique here just to reduce this, just to get practice with it. So this is the disjunction. So we have 4. We're going to factor the expression inside the absolute values. So this will be x minus 3/4. Remember, you always reciprocate whatever you're factoring. If there's no clear factor here of 4, or you could always apply this. It's always going to work. So again, when we multiply through by the 4 is absorbed and we get the -3. So now this is greater than or equal to 9. And so if and only if we get the absolute value of 4 times the absolute value of x minus 3/4 is greater than or equal to 9. Of course, like we had before, this just equals 4. So now we can divide by 4. So we have the absolute value of x minus 3/4 is greater than or equal to 9/4. So what's nice about this is that you just get practice manipulating the expression or the argument inside the absolute value, or sometimes we just say the argument of the absolute value, and we simplify it. And now we can apply the disjunction theorem. So we have x minus 3/4 greater than or equal to 9/4, or x minus 3/4 less than or equal to the additive inverse of 9/4. Now, again, if you don't do this manipulation here, you'll still get the same answer. It just means you'll have to do a little bit more algebra. So by cleaning up the algebra here, we make these easier. But it doesn't matter if you don't do it. Again, I want you to get some practice with this. It's important to feel comfortable with the absolute value properties. So at this point, again, we're just adding 3/4 to 9/4. So x will be greater than or equal to 12/4, which is just 3. And now, of course, we're adding 3/4 to -9/4. So x is less than or equal to, and in this case, we have what? A -6/4. -9 plus 3 is a -6. And of course, this reduces to -3/2 if we absorb the 2's that are available in 4 and 6. So now, of course, this is disjoint. So we have -infinity to -3/2. And of course, notice we got less than or equal to, so we get the bracket union bracket 3 to infinity. So be careful when you're working on these problems. Sometimes you forget the equal to. I mean, you're thinking, oh, that's not a big deal, but it is important. It is important because if we're using greater than or equal to, we're saying that we need the endpoints or we don't need the endpoints. And so that will change the way you actually type the intervals. Because if you have the equal to, you want to use the brackets. And of course, if there's a strict inequality, you use the parentheses. So be careful with that. It's very easy to forget that. So let me give you an example of how we might be thinking about symmetric intervals. So when you think about in the calculus, for instance, say we have a number line. I'll show you how we can think of absolute value in a way that may surprise you. And say we have the number 2, and we want to approach 2 from either side. That's how we think about limits. So when we consider approaching 2, we're thinking values greater than 2. Like on this side, we say 3, and we say 2 3/4, 2 1/2, 2 1/4, 2 1/5, 2 1/11. That is, we want to approach 2 from the right. And then, of course, if we're coming from the left, maybe we start at 1, then 1 1/3, and then 1 2/3, and then 1 4/3. Well, that's too big. 1 2/3, and then let me change the fraction, and then 1 4/7, 1 5/7. The idea is we want to approach 2 from either side in the standard limit without actually getting to 2. And that's a process that we have to define in calculus, which at first is very abstract. But once you start thinking about it, it will make good sense as you get more and more practice with it. So for instance, if we thought if we thought we want to approach 2, and then we were interested in not being, well, let's just say a distance 1 on either side. So maybe we would go here to 3, and we'd go here to 1, and we want to be in that symmetric interval about 2. So the symmetric interval results because from 2 to 3, we have a distance of 1, and from 1 to 2, we have a distance of 1. So we could say, how could we actually define this with absolute value? Well, now you can see it's very simple. If we want x, so we'll take x here, we want to live somewhere in the interval, we could say, well, x lives between 2 and 3, and x lives between 1 and 2, but of course we would want to include that. So for instance, we could say, well, what do we need? We need, let's think to this side. We say x element of 1 to 2, and I mean anywhere in that. So and then we would say x element of 2 to 3. Now that's kind of busy, and you're thinking, well, there's some repetition here because the distance between 2 and 3 and 1 and 2 is the same. So you could say, well, let's think about absolute value. So we could say, now we could say x minus 2 between 1 and negative 1. That is, think about this as a conjunction. So if x, let me use a red color here. We could think of x being in this part. And so the distance between x and 2 would be less than 1. And then, of course, if x were in this part, well, we would say the distance between x and 2 is greater than negative 1. Okay, so we go from here to here, and that's really not that good. But when we look at this, this is the other side of the conjunction theorem. So now we see the c is 1. We have the additive inverse of c there. So this is just x minus 2 less than 1. So the conjunction theorem allows us to go from the compound inequality into the more sophisticated inequality that utilizes the absolute value. So what we would say in this particular case is that, for instance, we say x minus 2 in absolute value is less than 1, or x is within 1 of 2. Let me say that again. X is within 1 of 2. That is, if it's to the right of 2 or to the left of 2, abiding by this, it's within 1. So not quite to 1, within 1, maybe it's a distance 4/5. Maybe it's a distance to 2 1/2. Maybe the distance is 12/15. Who knows? Or 1/19. So again, x is within 1 of 2. So this is how we construct a symmetric interval. And so when you actually write the calculus for something that looks like this, we could say that delta would be a positive number using a little Greek letter, and we could say C element of R is fixed. So now what we can do is we can think of the delta as being the 1 and the C as being the 2. So now we could write the absolute value of X minus C is less than delta. So we say X is within delta of C, just like we say X is within 1 of 2. And just like going backwards, this would mean that X minus C is less than delta or greater than negative delta. But now you can see here, if we just did one more step here, as I was describing, kind of from here, we've just got what? X is between 3 and 1. Now, that's not as good. I mean, we don't want that. I mean, that's like 1 to 3. That's when you put these together. But then when you consider the midpoint of this interval, which is 2, then you get the symmetric. So you can just think about taking any interval and making it symmetric. Or you can think about this, go this route, and then say, well, that's really what it's saying. But if you want it symmetric at about a number, then we need to do this. And so we could say the midpoint of the numbers 1 and 4, 1 and 3 would be their sum divided by 2, which is 2. So now when you do this, we have the same thing. We'll have C minus delta less than X less than C plus delta. So when you look over here, the 3, let me just write this down looking the same way. So here we have X and we have 2 plus 1 less than. Here, let me not bunch that up so much. So X less than 2 plus 1. And then, of course, here we have 2 minus 1. So when we look at these two, they're the same. I went ahead and added these numbers here, but when you look here, if we take the delta in this particular case to be 1, then we have the minus 1 plus 1, minus delta plus delta, and we have the C to be 2, 2 and 2, and then, of course, the X in the middle. So when you're working with a limit definition, all you need is a positive number, and you need X to be within a particular positive tolerance of C. And so the idea that is that by using the absolute value notation, we're actually setting up a nice symmetric interval. And of course, if you just drew your interval with the C and then wrote the rest of this over here, you have C plus delta, and you have C minus delta, and then X, of course, could live somewhere in here. So you get the same thing, and you're approaching the C from either side. So these are the same construction, and you can see how this absolute value notation using the conjunction theorem is extremely useful and extremely compact. So that's why we want to learn about absolute value. Now, again, this is not overly difficult, but you can see how the use of the absolute value is very useful and very elegant in the sense that we can write this to say a lot of stuff in a very compact, clean way. So as I've talked before, this conjunction theorem will be used widely in the calculus. And so if we can become better at using the absolute value, these theorems, namely the conjunction, all of these actually, and then the properties of the absolute value, we will be very well equipped to work with limiting definitions in the calculus. So I don't want you to think that absolute value is just something that's thrown at you without any regard to where you're headed in mathematics. Absolute value is a significant function, and we will define it as such, which we've done here. This is defining the absolute value as a function, and with an alternate definition here. So I want you to practice with the inequalities and the equalities. I want you to think about the properties of the absolute value, not just merely memorizing things, but working with them. Because if you think about the exercise we did here, being able to create the symmetric interval is very useful. And so if you think about this, choose your own numbers, choose another C, and then just go a distance on either side. Whatever you choose, maybe you'll do 1, maybe you'll do 2, maybe you'll do 3 halves with the same on either side, and then write the symmetric interval. This will be excellent practice to prepare you for more STEM mathematics. Okay, so I hope this has been interesting. I want college algebra to be a gateway course to prepare you for all of the things that you'll see algebraically. And then, of course, as you get to pre-cal, we will continue with a lot of these ideas, but we will also add the trigonometric functions. You will learn about logarithmic and exponential, but we'll add a little more detail. And then, of course, when you get to the calculus, you'll learn the full picture about the exponential and logarithmic functions. And then, of course, the trigonometric functions will play a big role too. Just remember, we do not do trigonometry in college algebra, but when you get to pre-cal, we will cover the trigonometric functions. And then what's nice about the calculus is that we get the complete story with the limits, with the derivatives, and the Riemann integrals. Remember, we will often think about limiting processes in college algebra and pre-cal as a precursor to calculus, because we want to understand what that means, and the intuition is going to be very valuable. Okay, well, I hope this has been interesting, and I will see you soon for another lecture. Take care.